Today, I am very excited to show you a pioneering research in sub-terahertz communication. Spectrum is a limited resource and the lifeblood for wireless communication. To enable the path towards 6G, we made spectrum expansion towards terahertz as one of our key research vectors. There are multiple benefits from expanding the available spectrum towards terahertz, including increased capacity, higher throughput, and lower latencies, which are becoming increasingly important to support new and enhanced applications such as wireless fronthaul, wireless fiber to the home, wireless data centers, and even 6G mobile broadband applications. In today's demonstration, we will be operating at 145 GHz over a 7.5 GHz wideband. There are challenges when moving up to sub-terahertz frequency bands. For example, the radio signal attenuates faster with distance. To address this, we will be using a similar solution as in millimeter wave by directing the radio signal into a narrow beam. However, we will not be using a large array beamforming antennas due to power inefficiencies when operating at the sub-terahertz bands. Instead, we will be using an innovative lensed MIMO architecture in a 4x4 configuration where each transmitter is outputting a 0.1 milliwatts. Like optical transmission, we use a lens to concentrate the RF energy into a precise beam. Another important benefit of lens MIMO is cost and power efficiencies. In terms of waveform, we're using something called DFT spread OFDM that provides significant better performance than regular OFDM in this spectrum band. Furthermore, with new coding techniques, extreme low power coding is designed to enable high throughput communication. In our first setup, we are communicating indoors in one of our office corridors. We start at a short distance, and as we can see, we are easily achieving over 100 gigabit per second speeds. If we increase the distance to 30 meters, we can still maintain very high throughput speeds. In our second scenario, we are operating at a longer distances. Again, we start at a short distance, achieving speeds above 100 gigabit per second. Even as we increase the distance to 60 meters, we can maintain very high throughput. Here you can see that if someone walks in the path of the radio signal, the throughput speeds drop, which is expected at this spectrum band. As we have seen in this over-the-air demonstration, sub-terahertz communication can provide speeds in the 100s of gigabit per second throughput. We are continuing our research to push throughputs toward the terabit per second era, while increasing coverage, supporting mobility, and improving power efficiencies. So please stay tuned.